Hi everyone. Today we'll be discussing the LeetCode problem of the day, implement router, yet another design problem. The question states that you are given a packets and you have to implement a router which will efficiently handle all the packets. So in the packets we have three attributes. The first is source from which it is coming, and the next is destination to which the packet is going, and also the timestamp at which the packet arrived. So in the router class, you initially are given a memory limit, which will denote how many, at max, how many packets that particular router can hold. And after that, you have an add packet. In that add packet, you are given source, destination, and timestamp. If a packet already exists with the same source, destination, and timestamp, then it's a duplicate, so we don't add it. In that case, if it's a duplicate, we will just return false. If it's not a duplicate, if it's not present in the router, we will simply add it in the router and then just return true. Now we have forward packet, which means that initially all the packets arrive in order, in increasing timestamp order. So when you have the forward packet method, you just have to return the first packet that arrived, which is in the router currently. The return type is vector int because we are returning three parameters: source, destination, and timestamp in the vector. Okay, and for Java, I think it's a list. Yeah. For Java, we just have to return an integer array. And after that, we have another method, get count. So this get count method will check all the packets with the particular destination, which are lying in the range start time to end time. Yeah, it returns the number of packets stored in the router. So it will only count all the packets that are currently in the router and not the packets which are removed from the router. Only the packets that are present and the packets which lie in the timestamp start time to end time, those packets will be returned. The count of those packets are written. Let's quickly go over the first example. We are initializing the router with max size as 3, and first we have add packet 1490, so we add this. Next we add 2, 5, and 90. After that, for both of these adding, we are returning true because it is not present in the router as of now. For the third packet 1, 4, and 90, we see that it's already present, so we don't add it and we return false. After that, we add 3, 5, and then 95. In the next operation, when we add 4, 5, and 105, the router is full. So what we do is we first remove the packet which arrived first, that is this packet. So we delete this and then we add the new packet 4, 5, 105. So currently we only have these three. After this, we have a forward function which will return the earliest packet in the router. So that is this 2590. 2590. After removing this, we are again adding another packet 5, 2, and then 110. Now we are at the count method. So it says you have to count the packets to destination 5 from timestamp 100 to 110. We have two packets with destination 5 with timestamp 95 and 105. Out of these both, only this packet lies in the range 100 to 110. So this is only considered. The answer for the get count will be 1 because only one packet lies in range 100 to 110 for the destination 5. Coming to the approach, For each packet, we have three attributes: source, destination, and timestamp. We can combine all of these and into an object packet, which will have all the three attributes. And to store the packets, we can use a queue, because all the packets are arriving in the increasing timestamp. And whenever we remove a packet, or whenever the router is full and we have to remove a packet, we remove it in the first in first out order. So for the first in first out, a queue is the best data structure. For that, now we create a data structure queue which will store all the packets. So the first packet is 1490. It will be converted into this packet object and stored in this queue. Next packet 2590. Now also we have a problem that the packets can be duplicated. So the first one 1490 and the third packet 1490 are duplicates. We should not add 1490 again in this queue. To deal with these duplicates, we'll just create a set. So in the set, whenever we have a packet, we just add it. 1490 is added, 2590 is added. Now coming to the third packet, we first check in the set. If it's present, then we don't add it. If it's not present, then only we add it. So the third packet is present in the set, so we don't add it. Now coming to the fourth packet, it's 3590. Coming to the fifth packet, here we see that the queue is full, so we remove the first element from the queue and we add this 45105. So this is what our data structure is so far: one set and one queue. Now we have a forward method. For this as well, we just have to remove the first element in the queue. So we just remove 2590 and then we return it. We return the array with source, destination, and timestamp. So this add packet and forward packet is done. After this, we add another packet 52110. Now coming to the get count. In this get count, we have to count all the packets with destination 5 in the timestamp 100 to 110. Now looking at this set or from the queue, there's no way that we can iterate on all the packets with this destination as 5, because in the queue we only can access the first element. So for this, we can take another map. In this map, the key will be a destination and the values will be the timestamps. So we have the destination 4 as a key first, and in that the timestamps will be initially 90, and then this is duplicate, so we don't add it, and that's it. For 4 as destination, we only have one packet. Now let's go for the 5 destination. For this, we also create a vector, a list. First packet is 90 for 5 destination. Then we have 95, and then we have 105. Yeah, for 5 as destination, we have 3 packets. I think we also have a destination 2. So 2 is the key and the value will be 110. While creating while putting all the packets into this queue, we also maintain this hash map where the key is the destination and the values will be a list with all the timestamps. Now from this, when we have the get count, we have the destination, so we can directly visit this value, and from this list we can easily say which packets lie in the range 100 to 110. So 105 lies in the range 100 to 110. But there's one more issue that uh, when we are doing get count, we should only count for the packets which are currently in the router, not all the packets in the router. Because if we see, first we added 1490, we added 2590, we skipped this, we added 3590. While adding 4590, we had to delete 14 and 90 because the router is full. So that means this 90 is a stale input. I mean, this 90 is already removed, so we should not consider this while checking how many packets are in the time frame. We only have to check these both because these both are actually actively present in the router. So to deal with this, for each destination, we need to know how many packets from the starting have expired. So for that, we can maintain another list, another hash map. So initially, for the 4 destination, the starting index is 0. For 5 destination as well, for starting index is 0. For 2 destination as well, the starting index is 0. Now, once we encountered this, once we had to delete this, once we have to delete this entry 1, 4, and 90, that means the starting index will no longer be 0 because the 0th index is deleted. So the new starting index will be 1. Now, when we delete this entry 2, 5, and 90, the starting index was 0, but we have deleted 2, 5, and 90. So we increase the starting index to 1. So that means whenever we look into this this list of destination 5, our actual active routers is starting from index 1. So 0, 1, 2. So from 1, we have to consider the list to see what all are in my timestamp. So we have one queue here and one hash map with a key as destination. The values are our list of timestamps. We also have a set to encounter the duplicates, and we also have another hash map to know to remove the stale entries, to know the starting point of the active packets in the router. Now coming to the exact get count, we are given start time and end time, and we need to return how many timestamps are lying in this range. So for this, we can't just iterate on all of this and count how many are lying in the range start time to end time. For this, what we can do is we can use a binary search. Currently our list is like this: 90, 95, 105. And in the binary search, we can use binary search to know how many elements, the element which is just greater than the start time. So the start time is 110. The start time is 100. So in this, using a binary search, we can know that this index 105 is just greater than 100. And again, similarly, we use another binary search to know the index which is just less than the end time. So an index which is just less than 110 is also this 105. So the valid packets are starting at index 2 and ending at index 2. So the total count will be end minus start plus 1. So in this case, it is 2 minus 2 plus 1 equal to 1. So we only have one packet which is valid. In the output as well, we have 1. Now let's go over the code. First, I'll be creating a class which will store the packets objects. Source, we have destination, and we have time. Here we are just doing the constructor. This what source equal to source destination. Yeah, so we have the class created. Now, as we discussed, we need one queue which will store packet, and we need a hash map. Also, like we need a hash set which will help us figure out the duplicates, hash set packets, and we need a hash map. In that, the key will be the destination and the value will be the list of all the timestamps. Hash set exists. And also finally we need another hash map to know where the index is starting, where the timestamp index is starting for each destination. Integer key is destination, the value is the integer. Let's say start index. Also we need a limit to know the maximum limit of the router. Now let's go. In this we will just initialize all of our data structures. You go to new linked list, exist equal to new hash set, and then map is new hash map. Similarly for the start index, and then limit will be memory limit. Once all of these are initialized, let's move on to the add packet. So the first step is we need to create the packet object. New packet source destination timestamp. Once we have the new packet, the first step we do is we check if the packet is present in the hash set or not. Exist.contains packet. If it's already present, we do nothing and we return false. Else. Also, here we are doing hash set.contains an object, but for the object we have to declare our custom equals method and also our custom hashcode method. So let's quickly do that. Equals. So for the equals, we want it to be we want all the source, destination and time to be matched. Packet so first we typecast the object to packet and then we just return source equal to packet.source and destination equal to packet.destination, and what else, time equal to packet.time, and also override. So this is the equals method. Let's also create the hash code. Return objects.hash source destination time. So in the hash set, while we add all these packets, it will be added based on this hash code. This hash code is generated with all these values. So if the packet is present, we are returning false. If it's not present, then first step is we just add it in the hash set exist.add packets. After that, we also add it in the queue. Now we will check. Also at the end, we just return true because we are able to add the packet. After adding the packet, we need to check whether the queue, the router is overloaded or not. So we need to check for the limit. So for that, if queue.size is greater than limit, that means we need to remove the topmost packet. So we can just get the packet equal to queue.remove. So once we are removing the packet, we need to update the index in our start index for the destination. So start index.put destination. The key is destination, and the value we just have to increment it. So to increment it, first we need to get the value. Index.get destination +1. While we do start index.get destination, this key might not be present initially. So for that, we can use get or default. If it's present, it's fine. If it's not present, it will return 0. So if it's not present, we will just put the frequency, the index, we'll update the index as 1. So from the next time, the index will be incremented 1 to 2 to 3 and so on. And then we just return true. And also we need to add the packet in our map, in our list for each destination. So for that as well, first let's check if the destination key is already present. Map.get contains key. If the map already contains the key, then just add it in the list. Map.get destination .add timestamp. Here we are just storing the timestamps. We don't need the entire packet object because we are only interested in the timestamps. Now if it's not present, we'll first create a list. Once we create the list, list.add timestamp, and then map.put key will be destination, the value will be the list we just created. So this finishes the add packet method. Let's move on to the forward packet. For the forward packet as well, it is simple. We just have to remove and return the topmost element in the queue. So let's just remove the element first. Queue.remove, and then return new int. The values will be queue.source, queue.destination, and then queue.time. But before returning, we also need to do some processing, such as in the start index, we need to increase the index, and we need to remove this from the existing hash set. So exist.remove packet. So from the hash set, it's gone. Now we just need to increase the index, start index. So for that, we can simply use this start index.put destination. We don't have destination here. packet dot destination. Okay, packet dot dest. And we also remove it from the exist. Yeah, and that's it. Also, this queue can be empty, and when we have the queue as empty, we just need to return an empty array. So let's just make a check for that first. If queue dot is empty, then return an empty array. Yeah, so this finishes the forward packet method. Let's finally go to the count. This is a bit complicated. Let's just get answer. Okay, we don't need this. Okay, we have a destination, and in that destination we need to get how many packets are from start time to end time. So the first step is we need to check whether the destination is actually present in the router or not. So if map dot contains key, if the map doesn't contain the destination, then we just return 0. We don't have any packets. Otherwise, we first get the list, map dot get destination. Once we have the list, we know the range. We need to get the range or range iteratable on this list. We need to do this because we can't iterate from 0 to list.length -1 because we have some packets that are removed. So that is why we need to check from the start index that what is the actual start index we need to check. So left will be, we can get it from start index dot get destination. Here as well, the destination might or might not be present in this hash map, so we can use get or default. So if if no packets from the destination have ever been removed, then the start index will be 0 as normal. If few packets are removed, then the start index changes. So we got the start left, and right will be simply list dot size -1. Now let's also create two variables. First, which will store the first element, the first index in this list, which is greater than the start time. So initially, let's set it as a large value, r+1, and last, let's set it as last is the first index which is less than end time in this list. Let us set it as l-1. Now let's do the binary search to get the first index. While l less than equal to r, to just visualize this, let's just take an example. We have 4, 6, 8, 10. We have this array, and let's say the start time is 5, end time is 9. So from start time is 5, end time is 9, we are interested in this part of the array. So here in the first binary search, we are interested in knowing the first index greater than 5. So if we have list.get m, if it's greater than or equal to our start time. Okay. So currently if our mid is at 8, and if this 8 this 8 is greater than or equal to 5. That means this index could be my answer, because we are interested in knowing an index which is just greater than 5. So 8 is my answer. So I will set my answer equal to mid. And also I need to move to the left, because it is true that 8 is greater than 5, but 8 is not the first index which is greater than 5. We can see the 6 can also be the first index which is greater than 5. So that's why we just move to the left, r equal to mid minus 1. Else, in the else case, suppose if our mid is at 4, so 4 is less than 5, so we just move to the right and see left equal to mid plus 1. So by doing this, we get the first index which is greater than start time. Similarly, we can simulate for the last index as well, but before that we need to reset our first and last index, because we are going to perform the binary search once again. But now in this case, we are interested in knowing the end time. So if list.getM is less than or equal to start time, we set, if it's less than or equal to end time, then we set last equal to M, and then we move to the right, left equal to mid plus 1. Otherwise, right equal to mid minus 1. Now at the end, we got the start time and the end time. Let's just return last minus first plus 1. We can also have a case where our start times are like this: 4, 8, 10, 12. And initially we are assigning first as r plus 1. So first will be here and last is l minus 1. Last is here. Let's say our timestamps is from 1, 3. Start index is 1. Start time is 1, end time is 3. So for this start time 1, end time 3, our values of L and R, the last and first, will not change. So at the end, last remains here, first remains here. That means this 1 and 3 is lying here. So no elements from this timestamp are lying in this range 1 and 3. So that means for this case, the answer should be 0. We can check that by doing if first is greater than last, because always first should be here and the last should be greater than first. But if we have first is greater than last, that means no timestamps are present in our range. So we just return 0. Let me test it. Okay. R equal to bit minus 1. HASH. Okay, what's the issue here? SRC equal to packet SRC and test packet dot test and time equal to packet dot. Okay, we just have to put double equal to. What's the issue now? Okay, packet is already defined here. So to remove another old packet, we can just rename it as old, and start index dot put destination. So here the destination will be old dot destination and not the destination, because this destination is of the new packet, but here we are removing the old packet. So the destination will be old dot destination. Okay. Any other errors? Okay, what is this? Packet dot source, packet dot destination, packet dot time. For this input, we have output 0, expected 1. Router. We're adding it. If a map is present, map dot get dot add timestamp. Otherwise, we're creating a list dot add timestamp, then map dot put destination comma list. If queue size is greater than limit, old packet we are removing. Okay, once we remove the old packet, we also need to remove the old packet from the hash set as well. Exist dot remove old. Let's hope it works now. Okay, we are removing it from the hash set. Start index old dot destination. So then we return true for the forward packets. If queue is empty, return empty. Packet dot destination. Start index dot get. I think the same issue here as well. We need to clear it from the hash set here as well, because we are removing this packet. We are removing the packet, name packet. Okay. Exist dot remove, and then we are returning packet dot source, packet dot destination, packet dot time. Let's quickly go the get count. If it's not present, return 0. Map dot get destination, L R first, last, m equal to L plus R minus 1. If it's greater than start time, we set first equal to m. We set R, otherwise we increase L. Okay. We need to reset the L and R values, not the first and last. That's a mistake. Yeah, let's submit. Yeah, it works. Finally, let's go the time and space complexity analysis. For the time complexity, we have the router initialization, which is constant operation. After that, we have add packets. In the add packets, we are just first checking in the hash set, which is constant. If it's not present, we are adding it in the queue, again constant operation. And also from the map, that is also constant operation. If the queue limit is reached, then we are removing it. Removing it is also a constant operation, and then we are just updating it in the also the start index in the hash map. So overall, this is also a constant operation. Similarly, for forward packet, it will be constant operation, because all we're doing is removing the packet and then also updating the hash set along with the start index. Now for the get count, for this we are getting a list. On the list we are doing a binary search 2 times. So for this the complexity will be order of logN. So the total complexity will be logN, order of logN. And coming to the space complexity, this is all the space we have created: queue, exist, map, and start index. And the maximum size these can go is equal to the router size. Is router size? In the constraints, yeah, the memory limit is 10 per 5. So the queue, the maximum size can be order of n, 10 per 5. Exist also, which is order of n. We also have a start index, which is for the destinations. At most 10 per 5 calls can be made to the add packets. So we can have at most 10 per 5 unique destinations. So this will also have time complexity order of n. And similarly for the map, order of n. So overall, the time complexity is order of n. Yeah. I've also written the code in Python. If anyone wants to view it, I'll just put it in the description as well. Hope it helps.